And welcome back, students. As we continue our next topic in programming with linked lists, we're today going to discuss that of iterators. So getting started with today's topic, when you have a collection of objects such as the nodes of a linked list, you often need to step through all the objects in the collection either one at a time and perform some action on each object, such as writing out to the screen or in some way editing the data in each object. Well, an iterator is any object that allows you to step through the list in this way. In the class materials, we have rewritten our linked list 2 so that it has an inner class for iterators and a method known as iterator that returns an iterator for its calling object. We have made the inner class list2 iterator public so that we can have variables of type list2 iterator outside the class linked list 2, but we do not otherwise plan to use the inner class list2 iterator outside of the outer class. So there's no plan for us to use the inner class for something like that. Now, use of the iterators for the class linked list 2 are illustrated by the program iterator demo, which we'll look at in just a minute here. You'll note that given a linked list named list, an iterator for a list is produced by the method iterator as follows: linked list2.list2 iterator i.listIterator. The iterator I produced in this way can only be used with the linked list named list. Be sure to notice that outside of the class, the type name for the inner class iterator must include the name of the outer class as well as the inner iterator class. The class name for one of these iterators is, of course, linked list2.list2iterator. All right, and before we move on, let's go pop over to Eclipse. And you can see here's our linked list 2 rewritten. Here is that public class list2 iterator. Of course, you have a private node position, private node previous. Here you have the constructor object itself. Here's a restart method, which we will talk about in a little bit. You have the next, you have has next, peek, add here. And we'll look at all these methods here in a minute. If we go look at the demo, here's where actual construction of these objects are. Of course, we have our linked list 2 list, and then we have our iterator right here. So of course we can add with the dot iterator. So I say like list dot add to start shoes, orange shoes, coat, etc. So all that right there will add those items in. So if I just run this real quick, just so you kind of see. All right, list contains coat, orange shoes, shoes. So we're adding those items in. Then, of course, we're going to delete out those items, and then we're going to add one in, etc., etc. All right, so it's a pretty basic, straightforward program. And we're going to look at some of these methods, and particularly with the concepts of addition and deletion of nodes, which before, when we talk about nodes, we've really only kind of dealt with like removing the head node. So now we're going to be able to kind of deal with some of those other nodes. So as we look at this iterators now, the basic method for cycling through all the elements in a linked list using an iterator is illustrated by the following code from the demo program. System.println list now contains i.restart, while i.hasNext, system.println i.next. The iterator is named I in this code. The iterator I is reset to the beginning of the list with the method invocation i.restart. And each execution of i.next produces the next data item in the linked list. So i.restart moves it back to the head position. i.next is getting the next position of the node. Now, after all the data items in the nodes have been returned by i.next, the boolean i.hasNext becomes false and the while loop ends because hasNext just checks to see if there's another link within the linked list. Now, internally, the local variable position will reference the current node in the list, whereas the local variable previous references the node linking to the current node. So the way to think about it is position is where you're currently at, and previous is where you were. Now, the purpose of the previous variable will be seen when you get really into adding and deleting nodes. In the constructor and restart method, the position, remember, was set to head, and previous is set to null because, well, if you think about it, you're going to start at the head of the linked list, and there is no previous spot because you're at the start, so that's why we set to null. So to determine if the end of the list has been reached, hasNext is going to return whether or not position is null. So if it looks at your current position and says, hey, this is null, well, obviously that has to be false, but we're going to return if position is not equal to null. It's either going to be true or it's going to be false. So to step through the list, the next method first is going to throw an exception if we have reached the end list. So first thing is look to, hey, are you at the end list? So if that has next, is false, throw a new no such element exception. There's nothing there, it's false. Otherwise, the method retrieves the string value of the iterator referenced by position within the variable to return, advances previous to reference the current position, and advances position to the next node on the list and returns the string. So string to return equals position.item, previous equals position, position equals position.link, and return to return. Now, one thing I want to point out is that Java actually has an interface named iterator that specifies how Java would like an iterator to behave. So actually, there is already an existing interface for this. You actually technically don't have to. However, when we look at this class that exists, or the interface that exists within java.util, the one thing you'll notice is that our iterators that we're creating right now don't quite satisfy the requirements for the interface to truly be part of it. But for the purposes of our learning here, they're in the same general spirit as that interface and could easily be redefined to satisfy the iterator interface. So you could do a little bit of tweaking, a little modification, it could happen. Now, part of the reason why we're doing it the way we are, rather than just jumping straight to using the interface, is it gives us a chance to kind of learn and understand how iterators work. And for our purposes, we're going to use the version currently presented today. All right, adding or deleting nodes. This is the big thing, right? You want to be able to add or delete a node. Well, to add or delete a node within a linked list, you normally are going to use an iterator, then either add or delete a node at the approximate location of the iterator. Now, because deletion is typically a little easier than adding, we're going to look at the deletion side first. All right, when you're deleting a node, the linked list, remember, is an object of the class linked list 2. So the variables position and previous are instance variables of an iterator for the linked list object. These variables each hold a reference to a node indicated with an arrow. Now, each time next is invoked, previous and position reference subsequent node in the list. And as indicated in our diagram right, the node at location position is therefore deleted by following 2 lines of code. Previous.link equals position.link and position equals position.link. So if we look at our 4 steps here, this is our existing list with the iterator positioned here at shoes. So we have coat, orange juice, shoes, and then of course we're pointing to socks. So here's head, here's previous, here's position. All right. So we're going to bypass the node position from previous. So I'm going to say previous.link equals position.link. And you can see that we're pointing this link here to point to socks instead of shoes. And then we're going to update position to reference then the next node. So position is equal to position.link. So this structure here is now going to point to where socks is. Now, technically right now, shoes is not being used. So Java's automatically going to recycle the memory allocated for it. And we'll talk about that here in a second with the garbage collection. All right, now this last diagram, because this might get a little confusing for you, remember this no longer exists. So it's pretty much the same thing, just we don't have the deleted node in there. Head is still a coat, previous is an orange juice, but position points to socks. All right, now in that display, you'll notice that next has been invoked twice. So position is referencing the node shoes, and previous is referencing the node socks. So delete the node referenced by position. The link from the previous node is set then to positions link. As shown also in the display, this removes the linked list reference to that node. The variable position is then set to the next node list to remove any references to that of the deleted node. Note, there are special cases that must be handled for deletion. First, if the list is empty, well, then nothing can be deleted, and the delete method throws an exception. It makes sense because, well, you can't delete if it's empty because there's nothing there. Second, if the node to delete is the head of the list, then there's no previous node to update. You can't say, hey, previous, you got a job to do. Previous doesn't exist. Instead, head is actually set to head.link to bypass the first node in the list and set a new head node. All right, now all this is going to lead to something called garbage collection because remember we've changed the links from where they're pointing in memory. So the pointers of those links were before, let's say, pointing at location 2, and we moved it to 4. It was like 2 to 3, but now it's going 2 to 4. So Java is going to kind of help us out here because garbage collection is a very important concept, and we might have talked about a little bit before, but in the scope of what we're looking at, as far as the linked list is concerned, that old node that we're no longer referencing is no longer on the linked list. However, as I've already mentioned, the node is still within the computer's memory. If there are no longer any references to the deleted node, then technically that storage that it occupies should be made available for other uses, whether it's other pieces of the program or it's some other process. We want to free it up. Now, in many programming languages, especially lower level languages, you, the programmer, have to keep track of items such as deleted nodes and must give explicit commands to return that memory that was allocated before for recycling. Well, this is what's known as garbage collection or explicit memory management. Now, the beautiful thing about Java, it's done for you automatically. Hey, good job, Java. Or, as sometimes it's phrased, automatic garbage collection. Garbage collection, great little thing here to kind of help you out with some of your memory management. Is it perfect? No. But garbage collection does help look and say, hey, this resource is not being used. I'm going to say, hey, you can reallocate that for something else. All right, we've already talked about deletion, so let's talk about adding now. So let's say this time we want to add a new node between the nodes named by previous and position. So in our display, you'll see previous and position are variables of type node, and each contains a reference to the node indicated with an arrow. Thus, the new node goes between the two nodes referenced by previous and position. The method next has been invoked twice, therefore to advance previous to orange shoes and position to shoes. So here's our existing list with the position as shoes. All right, then we're going to create a new node using temp equals new node, new data position. So here's our temp right here with socks. Then we're going to make previous link to the node temp. So before this link right here, we remember was pointing to shoes, but we're going to change where it's pointing from there to have it point to here. Okay, and you'll also notice that previous.link is equal to temp. So this link right here, of course, bypass here. So this can get a little confusing to look at. So if we redraw this, you'll see that it's now a linked list. And it's just as if temp had been inserted right into there, as if it had always been part of that list. So a constructor for the class node, in this case, does a lot of the work for us. It creates the new node, adds the data, and sets the link field of the new node to reference the node named by position. Now all this is done with new node, new data position. So that we can recognize the node with new data in it when we study the previous display, let's assume that new data holds the string socks. The following therefore gets us from the first to the second step. Temp equals new node, new data, position. So if we want to finish the job, all we need to do is link the previous node to the new node. So we want to move the arrow to the node named by temp. And then the following is going to finish the job. Previous.link equals temp. And the new node therefore is inserted into the desired place. However, as we noted before, the diagram in step 3 could get a little confusing if you're not kind of tracking where everything's going because there's a lot of arrows going everywhere. So we redrew it, like I said, in that fourth diagram, which is simply a lot neater visual presentation, even though they mean the exact same thing. All right. So to summarize, the following two lines insert new node with new data as its data. The new node is therefore inserted between the two nodes named by previous and position. Temp equals new node, new data composition, previous.link equals temp. Previous, position, and temp are all variables of type node. Now when we use this code, previous and position will be instance variables of an iterator, and temp is going to be a local variable. Now just like with deletion, there are special cases that do exist for insertion that have to be handled. So for example, if the list is empty, then adding is done by adding to the front of the list. If the position variable is null, then the new node should be added to the end of the list. All right, and that's going to wrap up the note side, folks. Hopefully that kind of helps you get a good grasp a little bit about iterators and a little bit more implementation with linked lists. So I will see you next time.